But it's not working, so I need to share my full screen rather. Perfect. Hello everyone and welcome. So my name is Babu. I'm basically working as industrial PhD at Babu, and I'm going to present some of my recent research results on impacts of data splitting techniques on the performance of perception systems. So just give it a second. Yes. So here is how it's supposed to go today, the outline. But rather go to introduction. So yeah, let's talk about data lake. So when we typically split the data set into training, validation, and test set, so we might end up with this kind of situations where we have lots of similar frames, and some of the similar frames go to train set, and some of them go to either validation or on the test set. And that's how the data in validation or test set is exposed to the model that is trained. So in that way, instead of generalizing the model training, the model kind of memorize the pattern of the data. And that's how it performs really good in validation and test set when it is tested in the lab. But it's not the same case when it comes into work in the real-time systems. So that's why data leak is a very big problem to address. And so yeah, so it's a sorry. Excellent. So yeah, data lake, which is a very common problem and often overlooked, but it's very crucial problem for development and deployment of the machine learning or the deep learning models to be specific. So let's talk about some backgrounds. So yeah, so data leakage could be avoided if we choose the right way of splitting the data into training and testing, so that the data in validation or test set is not exposed to the train set. So that's why we conducted this study. We considered a new data set from a real driving scenario called Cirrus. It's a very recent data set. That's why we were interested into it to check different splitting techniques. So we basically investigated 6 different splitting techniques on the same data set. And I want to show some results, but so our research questions are like this. So we're interested to see what kind of data split techniques tends to leak data, and what kind of splitting techniques are suitable or can protect us from occurring data leak problem. So I can show a graphical overview of my whole study. So what we did here, we took the data Cirrus images, and we used the inference of a pre-trained model to generate some 2D levels for each of the images. And then we applied different data splitting techniques on these images with the labels, and then we examined we evaluated the splitting techniques with the YOLO V7X model, which is the recent version of the YOLO family. So yeah, then we evaluated the performances on different splits of the data. So our experiment design was pretty simple with 3 simple steps. These are we prepared the data into trained, validation, and test set. Then we trained the YOLO V7X model with our trained data, and then we evaluated the trained model with our validation and the test data. So before going into the results, I want to show some insights of the whole data set. So when we generated the labels, we found this kind of class distribution. So we found 7 unique type of objects in our images, and you can see that majority of them were car images. But we moved on with this data, and then so to introduce this Cirrus data set, Cirrus contains 7 different folders, and each folders contains around 897 frames, more or less. So in total, it ended up around 6,200 plus frames. So what happened in each of the folders, they have different root scenarios. And from now on, we call them sequences. So we had 7 sequences of frames in our data set. And based on that, we started applying different splittings. We call it treatments. So our first split or the first treatment was, we call it 3-2-2. That means 3 of the sequences went to the train set, 2 of them into validation set, and 2 into test sets. And how we choose which sequences will come to the train, which will go to the validation. So we found 10 different trials, 10 different types of combinations of the sequences to generate to do 10 times the same experiment, and then we took the mean of the results. And similarly, we took another sequence-based split, which we call 5-1-1. That means the 5 would be in the training set and the 1 in validation and 1 in test set. So we repeated these 2 also for 10 times with 10 different combination of the sequences, and then took the mean to compare with the other splits. So the third one was the frame-based. So we call it 4 versus 1. That means when we have sequences, we have sequential frames in each of the sequences, right? So we took 4 versus 1. That means consecutive 4 frames. We put them into train set, and the 5th one would go either in the validation set or in the test set, and that was random. And we did it for all the 7 sequences like this. That's how we created the validation sets and the train sets. And for the other, I'm just introducing the 6 different splits first, then we'll jump into the results. So this was a bit unique. So we designed as car versus snakes. So what we tried to do, we found all the images that contains only cars, not the other type of objects, and then we put them into the train set. And the other images with mixed objects, like with cars and other stuffs having there. So we put them into either validation set or the test set. And the 5th one is the similarity based. So by similarity, we meant image similarity. So we measured similarity. We created 3 clusters based on the similarity values. And then we labeled 3 different clusters into train set, validation set, and test set. And we did the same thing with the dissimilarity as well. So instead of considering the higher values, we just considered lower values to create these clusters. So these are the 6 different splits introduction. But then, so on which value we want to compare the 6 different splits. So for that, we decided to go with the MAP, mean average precision. So we found that most of the computer vision researchers find this matrix helpful when we have imbalanced class distributions. So now comes the results. So we repeatedly keep saying that for treatment 1 and treatment 2, for split 1 and split 2, we did 10 trials. That means 10 different combinations. And we were interested to see that how the results are distributed for both the validation data and for the test data. So in the left side is the validation, and in the right side we have the test results. And we saw that it's pretty much similar distribution. So these different colors means different classes, different objects in our data set. And the individual class accuracies are pretty much distributed quite similarly for both the validation set and the test sets. So we try to show similar results for the 10 trials for the treatment 2. And we saw that it's also pretty much more or less similar distribution. That means it's quite working. Only consider 10 trials and took the mean. Sorry. This kind of whole summary of different splits on the evaluation dataset or the validation dataset. So it's quite interesting to see, because when we did the frame-based, we intentionally put some similar data to both train and validation set to make a link, right? And then we also found in the results that the frame-based splits showed quite high accuracy, or the mean average precision value is pretty high. And it also happened for the dissimilarity based, because in dissimilarity based we also try to intentionally leak some data, because when we clustered the data based on dissimilarity, that means some frames similar to these frames are available in the validation and test set. So it should be recognizable. The data is in a way is linked to validation and test set. And we also found that that was also performing very high. But the most surprising thing was for the similarity based. And similarity based split showed very high results, but our perception says that. So when we compared the similarity of the images, we focused on the pixel level similarity, and we had a very high resolution images. So when we took the minimum of the pixel level similarity, so it didn't like distributed very high. How to say it? But yeah. So although we are clustering the images based on similarity, but still, so the similarity values are not distributed quite in a high range. So it was very congested, and that's why even though we are considering the similarity based splits to create the clusters of the similar images, but still it was performing quite good. And another thing was about the object based. So it showed the least performance, and it shows that we cannot be restricted too much to avoid data leak, because if we try to train our model with a particular class and then try to see how our model is performing in a mixed environment, so we can see that it might not perform well. So in that case, we can conclude that we cannot be too much restrictive to avoid data leak. But the other two, the sequence-based splits, 322 and 511, they are performing quite standard. So we can conclude that. So we can say that they somehow avoid data leak and performing quite like realistically. So yeah. So as I said, so our similarity-based splits and the frame-based splits showed very high performance, and we already know that they are more leak-prone kind of splits. And the 322 and the 511 seems like the safest choice. In that way, we are avoiding data leak, as well as we are having quite marginal performance as well. But when we intentionally choose the object-based, so it's kind of biased split. So the model is trained to know only one kind of object, and when it is in the mixed environment, so it might have lots of false positives. For example, if we have cars, if the model only knows cars, but then it might be confused in the real world that it might say the trucks or the buses as car as well, because they have quite similar structure. And the dissimilarity-based split also showed high performance because we have the pixel measurement bias. So when we consider similarity of the frames, so we might need to think about some other metrics rather than the pixel level similarity. I think that's all. I'm a bit fast today. Yeah, that's all. Thank you very much.
Okay. So questions or comments, Jonathan?
Are there like any sort of threshold values you can use to determine there's been a data leak? So, for example, imagine that you're the leader of a country or something, and there's like some approval rating poll, you get 80%. That probably means you're a great president. But if you get 100%, that probably means you're a chief woman or something. Like, if there's some sort of similar thing we can use.
I think it's very hard to determine this kind of threshold, because even though your model is performing 80%, there could be data leak as well. So it's very hard to find that threshold. And also it's because of the different, it's because of the variation of the data. So for example, when you change your location, so the data might be changed. And let's say we train a model to detect the road conditions or the road environment it knows from maybe from Europe, but when you go to America, it might be changed. So yeah, it's very hard to, I think, find a threshold value to know how if there is data leak or not. But usually what we do is, yeah, if the model is performing extraordinary, like 98% accuracy, so that means there is something wrong. So it's not a realistic performance, like, right? So yeah, but that's how usually we detect right now. But so far, I don't know, is there a way to find the threshold or not?
The sort of upper limits.
Yeah.
When you're
I mean, that's what you're asking is what we started the study with, right? So this yellow bar over there was what the company used for production systems. And everybody knew it's not perfect, but something had to be changed. And then the question is, how do we do it? We started with the dark blue one with the similarity base. So basically tried to calculate similarity between images. But then, as Babu said, the distribution in this similarity measures was very, very narrow. So finding a good threshold was almost impossible. Not because the metric was wrong, but because the images are high definition images, color images. So when you try to average the differences in the pixel density, the averages will be very small, by the law of big numbers, basically. And then we started looking at the orange one also, the object detection. So for example, because this is an object detection task. So if we train the model to detect cars, how good it's going to detect cars later on if we basically take away all the other objects in the images or ignore them. And it turns out that it's really bad regardless of the split, right? And then we said, okay, then how about we take it more related to, you could say maybe geographical location, right? So you have one sequence when you drive on one highway, and then you take another sequence when you drive on a completely different highway or in a car or in a city environment or country road, so to say. And then those two top bars are basically those scenarios. And then you see that the performance is quite different. I mean, that's probably those two bars at the top are probably the most representative bars. That's how good the model is. And it's what good is it like 0.659,
yes,
0.6, right? Versus the optimistic production system would say that it's 90% accurate or correct. So there's quite a big gap how much the model was boosted. And Babu's next study is to actually try to look for metrics to measure data leaks.
Okay.
Because right at the moment, the metrics that you have are only on the object identity. So basically, if it's not exactly the same picture, exactly the same file, then it could be put into different files. But if you take consecutive frames from a highway, I mean, if you drive 5 seconds or take 2 seconds between images, they will be physically different, but optically they will be very, very similar. Okay, the cars in the pictures may be farther or closer. And that's the big problem that we try to solve, to find the kind of metric to measure some sort of data leak. Because obviously the pixel level similarity is just not working. And object level similarity is also problematic because it's you have to have exactly the same classes of objects. And what Babu showed at the beginning, the distribution of objects in those images is usually very highly skewed towards one class. So the Cirrus dataset is Volvo Cars public dataset from driving on highways and country roads in California. So a lot of images, but it's Volvo Cars, so it's cars for highway driving. But pedestrians or vulnerable road users are just not there. So that's the golden goal of what we want to achieve, but still a lot of studies that we want to do. We thought it would be so simple that just take some sort of image similarity, but it's not as simple as it looks.
In real world, it's a bit complicated.
And now you have a new data set that you work with. So you work with a data set that's also annotated.
Yeah.
But then, of course, that data set is not those kind of images, but it's a fisheye camera. So it's fisheye shape. And then the annotations are not exactly the same format and so on and so on. So it takes some time to actually even parse the data, so to say.